Okay, hey everyone. Welcome to Gen Chem Test 4 review. We're going to get started now, and it's 7:30. If you have any questions while we are going through the PowerPoint, the review section, just put them in the chat, and we will try to get to them, either me or while I'm talking, or someone in the chat will help you out. So yeah, let's get started. Kevin, if you want to go ahead and come on.
Hello everyone, it's 7:31. We're going to go ahead and start our General Chemistry 1 Test 4 review. So if you haven't yet, please mute your mics if you've arrived, and we can go ahead and get started with the review. Okay, so one of the first topics covered is exactly what is a chemical reaction. So as you guys will probably remember, discussing in class, the law of conservation of mass. That is the idea that matter within the universe is neither created nor destroyed. It is simply rearranged from one form into a different form, known as reactants and products. And the typical formula you'll see is right there. It's like reactant A and reactant B are combined to form reactant C plus reactant D. And then the little smaller letter in front of the larger letter represents the coefficient, meaning how many moles of that coefficient you have, or product. And so there are about 5 types of main reactions you want to consider. There's a combination reaction, wherein 2 reactants or more will combine to form a singular product, just one product. And then a decomposition, which is the opposite of that. That is when you have a single reactant which breaks down into multiple constituent products. And then you also have a combustion reaction, which you have a reaction of a carbon or hydrogen product typically, and it burns in the presence of oxygen, so you typically need heat along with oxygen. And it will always form carbon dioxide and water, so that's a special one. You know, the products will always be CO2 and H2O. And then finally, secondly, you have single replacement, meaning you have, say, two reactants. One is a compound and one is a singular like atom, and it just swaps pairs. So one of the atoms comes out, the other one comes in, and that's what you get on the product side. And then for double replacement, basically it's you have 2 reactants and they're both compounds, right? And they both have different partners. And they basically just swap partners. So if compound A was made up of A and B, and reactant B was made up of C and D, they swap each other's partners, so you have A and C and B and D on the product side. And then also state symbols will be important to keep in mind, usually later on. So you just have 4 states that we're concerned about here: solids, liquids, gases, and these are pure forms. Aqueous, meaning it's been dissolved within water. Okay, so for balancing equations, this is also considered to be like stoichiometry. So remember, with the law of conservation of mass, you want to have the equal number of reactants, moles of reactants, or not moles, like atoms on the reactant side as you would on the product side. So you do this by basically changing the coefficients so that they balance out correctly. You cannot change the subscripts. Any of the smaller numbers, like behind a atom, you cannot change. You can only change the coefficient. And so once the reaction is balanced, you can use stoichiometric ratios, and basically the ratios between different moles, between reactants with a reactant or a reactant with a product, and they can be used as conversion factors whenever you're doing dimensional analysis. again, this is what I was talking about, the stoichiometric ratios. So basically, if you're trying to get from like substance from the reactant side on the left, going to the product side on the right, you're going to need to convert to moles, and then using your coefficients from the balanced chemical equation, that's what we were talking about, you have to figure out how to be able to balance it in order to help convert into products. Or you can go backwards from products into to reactants as well. But it's all dependent on being able to use a correctly balanced chemical equation. Okay, so limiting and excess reactants. If you guys recall, you won't always have the exact number of reactants you need to make like a complete reaction. Most of the time, you'll typically have one reactant that runs out first. And that's going to be called a limiting reactant. So it's kind of used also in industry to try to make sure a reaction goes to completion. Typically, the limiting reactant will be the more expensive one to make sure it's entirely used up. And the other reactants that are left behind are going to be considered the exit reactants because you still have them left over. So if you see in the image, the diagram I have there, you have two reactants. It's the red dots and then the green pair dots. And at the end of the reaction, on the other side, the product side, you'll see that there's a couple green pair dots left over. That means they're the excess reactant, so you know the red one was going to be the limiting reactant. Okay, going on to yield. So there's three types of yields that you need to be concerned about. A theoretical yield is the yield that you should get in theory if you do all your calculations correctly. That's basically the yield that we've been working on throughout the semester. Whenever we do our calculations, it's all theoretical and shows us what we should be getting. However, in our lab setting, it's not always the case because there are a numerous number of ways you can create an error, such as accidentally releasing gas from a container, loss of product, accidentally having contamination that comes into your reaction vessel, and just like other types of errors like faulty equipment, stuff like that. So that will give you your actual yield, and the ratio of actual yield over theoretical yield and 100% is going to give you a percent yield. So having a 100% yield is our best case scenario. We understand that's not always the case. You can always have more or less depending on what kind of errors you made in lab. Okay. So next, talking about electrolytes. So an electrolyte is basically any kind of substance that you put into a solution, it'll break apart into ions. And this allows for water to be able to conduct electricity. So because they're ions, the electricity, the current that's sent through water is able to use these ions to travel through the water to wherever it needs to go. And strong electrolytes are substances that will always break apart 100% and are therefore good conductors of electricity. So some of these you can think of are any kind of ionic compounds, like salt, like like your regular table salt, NaCl. That is like a strong electrolyte because it breaks apart into Na plus, Cl minus, and then you have your strong acids and strong bases. We'll go over that in the next slide. But strong acids, strong bases will fully dissociate. They break apart into constituent ions, and there's also weak electrolytes. So we also have compounds that don't always fully dissociate, and for the most part, they're usually weak acids and bases. So weak acids and bases don't fully dissociate. They will break apart, but some of them will also like to stay together as a compound. And these, the idea is that mostly the unionized form of the compound will exist in solution. And so they're not as good. So they will still conduct electricity, but not as effectively as the strong electrolyte would. That's the idea. And then a non-electrolyte is a substance that just does not conduct electricity because it doesn't break apart into ions. So if you take a look to the image on the right, you'll see the difference in conductivity of the three types of electrolytes. So the non-electrolyte conducts no electricity, the weak electrolyte conducts a little bit, and then strong electrolytes will give you the most electricity. Okay. Okay. So strong acids and bases. So like I said earlier, they are strong electrolytes, so they will dissociate completely. And the strong bases are typically made of group 1A and group 2A metals. So if you have a hydroxide, remember, the OH, and you combine that with any of the group 1A metals, excluding hydrogen at the top, of course, like potassium, lithium, sodium, you can form a strong base. And then most of the group 2A metals as well. I have the list over to the side. You can take a look at that. And then remember, for your strong acids, there's going to be 7 that we need you to know. And they're going to be HCl, HI, HBr, H2SO4. It's like a special one because the first ionization, so H2, right, means there's 2 hydrogens that it can give up. But the first hydrogen it gives up is the most easily given up. So that's what makes it a strong acid. That hydrogen, it's going to become HSO4 minus. And this second hydrogen will not be given up as easily. HSO4 minus is a weak acid. H2SO4 is a strong acid. I wanted to point that out, be clear about that. So continuing on with the list, we also have HNO3, HCl4, HCl3, and yeah, that's 7. Okay, and so there's types of definitions of acids and bases that you guys need to remember. There will be a third one for Gen Chem 2, but for now we're just focusing on these 2 definitions. So you have the Arrhenius definition, which was the first definition to come about. So the idea is that an acid is any compound that when placed in water will increase your concentration of each plus ions in a solution. And then conversely, if you have a base, as any substance that you place into water will increase the OH minus concentration in solution, such as KOH, it's going to break apart into ions, K plus ions, OH minus ions. And then your second definition is the Bronsted-Lowry. So Bronsted-Lowry acids are any substances that will donate a hydrogen to another compound, versus bases which will accept that hydrogen. So whenever you're looking at a reaction, if you see from the reactant side and the side is changed, and you noticed a donation of hydrogen, like one substance lost a hydrogen, so you know that's going to be your acid, and then one substance gained a hydrogen, that's going to be your base. And looking at the page on the top there, the idea is that most acids and bases, strong acids and bases, will produce water and a salt. So a salt being 2 ions put together that will break apart into solution. Like NaCl, what we know as table salt, and then KBr is also considered to be an ionic salt. Okay, there's also 3 types of equations that we're also going to be looking at. So our molecular equation, you guys have seen this time and time again. This is just the regular type of equation. You have all your compounds written out in your chemical formulas. This is the normal way to write your chemical equations, just products and reactants and their appropriate coefficients. So whenever you're doing an ionic equation, you want to show that the reaction is occurring in solution. So it's in an aqueous solution, so therefore all the solids that are soluble will break apart, and therefore you write out the ions. So if you had like NaCl as a reactant, you want to break up NaCl into Na plus and Cl minus. So those are two different ions, two different reactants in solution. And make sure you also include base, so aqueous, aqueous. And then for net ionic equation, this one, it's important to know what spectator ions are. So spectator ions are ions that will show up on both sides of the equation, on the reactant and the product side, but they do not participate in the reaction. So if you see, whenever you create your ionic equation, and you have ions that show up on the reactant and product side, and they have the same state, that means they did not do anything, they've just been in the reaction. You can cancel those out. Once you canceled out all of your spectator ions, you can rewrite it with whatever is left over, and that's going to be considered your net ionic equation, because it will typically show you a reaction occurring between two ions. I mean, it's usually going to be a solid product, which is together and does not break apart into ions. There. Here are some examples. Like I was saying, the molecular equation at the top is just your normal standard equation, but when you're breaking it apart into full ionic, it's also called full ionic, or just regular, or just ionic equation. You just write out all of your ions as it would be in solution, and then you want to cross out any that appear on both the reactant and the product side the same way. So look at NO3 minus and K plus on the reactant side. They're both aqueous, they're both separate, and on the product side, they're both aqueous, both separate, so you can cancel those guys out. However, if you look at silver plus aqueous on the reactant side, and then silver chromate on the product side, you'll see that they're different. You have Ag plus aqueous, and then the silver chromate solid. And you can see that there has been a change in state, and they're not technically not the same compound, because one is an ion, the other is a molecule compound, and so therefore you have to leave it in there. So for people talking about the coefficients, whether we should write those in, I want to say, yeah, if it helps you keep track, go ahead and write that in. This example just do not have it written in. So I would put like a 2 in front of the silver plus, and then a 2 in front of the NO3 minus. It'll help you keep track of where your coefficients are. But down here on a net ionic, that's the correct way we want to write it. So we do have 2 silver plus still. And all our spectator ions have been canceled out. All right, I will pass it over to Naresh.
Okay, thanks, Kevin. So we're going to be talking more about the next chapter, I believe chapter 9, starting with redox reactions. So redox reactions, these are a special type of chemical reaction in which what's important is that electrons are transferred over from one reactant to another. From one reactant to another. So redox, what it stands for is reduction oxidation. So the red, reduction oxidation. So there's two reactions happening together, two half reactions to form one full one. The same way that precipitation reactions exchange ions and acid-base neutralizations exchange hydrogen ions, as we saw earlier, redox reactions are another reaction just like that, only they're with electrons. So in this example that we see over here, we have zinc, and zinc is being oxidized. We know it's being oxidized because it's losing electrons, and copper is being reduced, and we know that because it's gaining electrons. Well, copper ion is being reduced into copper solid. And adding these two together gives us the final redox reaction equation at the very bottom. Okay. So as I mentioned, oxidation is loss of electrons. A common mnemonic used for that is Leo, like Leo the lion. So whatever is oxidized is also the reducing agent, and we say this because because these reactions are always partnered up together. So whatever is being oxidized has to be causing the reduction of the other reactant. And similar with reduction, reduction is a gain of electrons, so Gur. So the mnemonic goes Leo the lion, Gurs. And gain of electrons, so whatever's being reduced is also the oxidizing agent. And this is because whatever's being reduced, it's in partnership in the reaction with the one being oxidized, and it is causing the oxidation of the other reactant. And the whole reason why these reactions take place is because different atoms of different elements, they have different tendencies to gain electrons. And this we know from electronegativity and other things as well, other periodic trends. But this is the basis essentially for redox reactions. And remember, always remember to balance these equations, and that includes the electrons that are transferred in these. So, and that you do that by doing stoichiometric coefficients to balance each of the half reactions. So if we see on this example that we have over on this page, we have calcium is being oxidized into calcium 2 plus, and we have oxygen being reduced into oxygen 2 minus. So we had to multiply the top half reaction by 2, and that's why you have C coefficients of 2 on the calciums, and you have 4 electrons, and that way the 4 electrons can cancel out with each other to give us a final redox reaction shown at the bottom. Oxidation state or number, this is a way to basically show or to determine what is being reduced, what is being oxidized, whether you have a redox reaction taking place. So when we think about ionic compounds, we know that ionic compounds involve the direct transfer of electrons, right? And this was, we talked about this earlier in previous units. And when we think about covalent compounds or molecular compounds, these do not involve a direct transfer of electrons. We're actually sharing electrons with the covalent bond. So each covalent bond is 2 electrons that are shared. They're not transferred. They're shared between the two to form a bond. 2 atoms, I mean. So there's no complete transfer of electrons, but there is a partial transfer in the sense that they're sharing these electrons. So what the oxidation state or number actually tells us is the charge an atom would have if the electron transfer was complete, as in if it was like an ionic compound. So we're almost treating these covalent compounds like the electrons being transferred were ionic, and that's what's taking place. So there are various rules that we will discuss for assigning oxidation states or oxidation numbers. We'll see that on the next page, but over here is a brief schematic of how we typically write these out. So because H2, hydrogen gas, and fluorine gas, F2, are just uncharged singular or diatomic elements, we just have 0 for both of them for oxidation states. That's a constant rule. And then for 2 on HF, we have -1 on the fluorine and +1 on the hydrogen. And that's because overall the oxidation states should balance out to the charge of the overall compound. Right, so this is more of what we were talking about. A change in the oxidation number is how we're going to indicate a redox reaction. When we see that something is losing electrons, that means that it should be gaining a more positive charge. So something being oxidized is going to go from its solid state. If it's a metal, it's going to go from its solid state into its ionic state because metals form cations. And then for something being reduced, it's going to be gaining electrons, right? So gaining electrons makes it more negative, and that's typically how it's shown with metals, is that the ion of the metal, the cation, like calcium 2 plus we saw earlier, that's going to gain electrons and form calcium solid, so solid calcium. So 2 main rules for assigning oxidation number. We kind of discussed this earlier as well. The first one is that the oxidation number of any element in its elemental form is 0. So elemental form is like how this H2 is a diatomic. Hydrogen is diatomic in its elemental form. Same with F2. So that's why it's a 0. That's the overall charge of the entire diatomic molecule. And then oxidation numbers in any chemical species must sum to the overall charge on the species. And same, this still applies to that first rule as well, right? For diatomic hydrogen, there's no overall charge, and that's why we have 0 for it. But if we have a ion, then the ion should have a charge on it. Okay, so these are some basic rules for determining the oxidation states or oxidation numbers. And so we can go down the list. The first one is fluorine. Fluorine, without any exceptions, always has oxidation number of negative. So whenever you're assigning these numbers, you want to look at each individual atom on the molecule and assign them one by one. So starting from the topmost, if you see fluorine in the molecule, one of those atoms, you know it's going to have -1 for its oxidation number. Next, after that, you know any group 1A or 2A metal could have a +1 or +2. And 1As will have +1, and 2As will have +2. And remember, this has to do with the valence electrons that are present. Next, hydrogen has +1, but there are exceptions. So basically, to summarize the exceptions that you see on the right, basically anything lower is beaten by anything above. So if the fluorine and a group 7A are together, you're gonna have fluorine it's gonna overrule the oxidation state of a group 7A. So you just go in order down listing them. Then after hydrogen, we have oxygen is -2, and then group 7As, except for fluorine, are going to be -1. Fluorine is just an exception on there because of its high electronegativity. And the activity series, this is going to be a list of metals and hydrogen that are arranged from top to bottom in order of decreasing ease of oxidation. So looking at this chart, you actually do not have to memorize this chart. It will be given to you, I believe, on the test. But going from bottom to top, the topmost elements found over here, like lithium, potassium, barium, these are more likely to become oxidized. So the right side, you see the oxidation half reaction, meaning that lithium, if it's found along with a lower metal, lithium will oxidize and it will, and the other lower metal will become reduced. There was a question about where to find the review session afterwards. It's uploaded to YouTube. So a metal higher in the series are more likely to become oxidized, and they're also found oxidized in nature. So if you think about it, whenever you think about gold, we don't think about gold as a component of or one atom in a molecule. Gold is usually just found gold, like a precious metal in the earth, and that's why it's just found as gold alone. It's not found in its ionic cation form of gold 3+. Same with platinum, same with mercury. Mercury find in thermometers, silver, copper, all these things. All these metals, especially toward the bottom, they're found in their elemental forms. They're not found in their cation forms, and that's because they are so low in activity series. And then the ones higher up, like potassium. Potassium, lithium, barium. These are all really reactive and violently reactive sometimes metals. So potassium, it's almost found as like an ion in the body. Potassium solid, lithium solid. These are like pretty much explosive metals. They're very, very reactive. So metals higher in the series will replace metals that are below it in the replacement reactions. That's a question in the chat. Metals higher in the series will replace metals that are below it in the replacement. Well, what the activity series tells you is which metals are more likely to oxidize. So if I was to find lithium, solid lithium, that's reacting with gold 3+ cations, then gold 3+ cations, lithium is going to transfer its electrons. Gold 3+ is going to, sorry, I'm getting this mixed up. Lithium is going to transfer its electrons over to gold 3+ cations, and that's going to reduce the gold cations into gold solid. That's what that means. And then the lithium in reverse is going to become lithium plus cation. I hope that made sense. Activity series does apply to a metal and a metal. Yes. So molarity. Going on molarity now. Molarity is the constant. So solutions can have different concentrations, and this can have various effects on reactions, including redox reactions, as we'll find later on with more things. But molarity is a way to measure. It's one of the measurements of concentration, and this is the number of moles of solute per liter of solution. There are other ways to measure concentration, such as molality, and there's actually more as well, but for now, molarity is going to be the one we're going to focus on. So to calculate the molarity of a solution, what we have to do is we have to divide the number of moles of the solute and the solute by the volume of the solution in liters. So remember, every solution is made up of two different compounds. Often we're talking about aqueous solutions, so there's going to be something dissolved in water. So the solute is whatever's found less, the one in less concentration. So I could have a solution with a solute for potassium. There's some potassium dissolved, electrolyte dissolved into the solution. A dilution is the process of preparing a less concentrated solution from a more concentrated one, and this you see very often with the equation M1V1 is equal to M2V2. It's an easy way to determine the dilution of however much the dilution required to form a more dilute solution. Excuse me. So this is a schematic of a dilution, right? So before the dilution, you have a very concentrated solution with a lot of solute particles per unit volume. And then once you dilute it by adding water or possibly whatever other substance is dissolved in, it would become less concentrated. You'd have fewer solute particles per unit of volume. So solubility rules, this is something you will have to know, and it's not going to be given to you like the activity series is. But what's important here is that some ionic compounds are soluble, but others are not soluble. They're insoluble. And this is not technically absolute. There are different degrees of solubility, but for now, solubility is considered absolute for Gen Chem 1 at least. So there's just some guidelines here. You can look at those yourself if you haven't already seen them too much. But there's certain cations that can be found in elements such as the alkali earth metals, that's group 2A, or the ammonium ion. Whenever those are found in there, along with nitrate ions, chlorate or acetate, that makes the overall compound soluble, always. And there's some more with some exceptions, and you can read through that. This is just a short mnemonic you can use for solubility rules. It's like NAG-SAG, and there's exceptions over here as well with the sulfates and group 17. So a titration is a analytical technique that allows you to determine concentrations of unknown solutions called your analyte. So usually this is something you do in Gen Chem lab. I guess that's not really an option right now, but it's a really common analytical technique that's done. So what happens is that you have a solution of accurately known concentration, also known as standard solution, or the titrant, and this is added gradually to another solution that we are trying to determine the concentration of. So we have an unknown solution of unknown concentration. And we're going to keep adding this known concentration solution until we have a complete chemical reaction. So remember, for titrations, you always want to make sure you use a balanced equation, as with everything in chemistry. And titrations are particularly relevant for us for acid-base neutralizations. There's been a question, where do indicators play a factor in titrations? So it's a good question. Indicators, what they are is that we add them to the analyte solution, as we'll see later on, and that allows us to determine the endpoint of the titration. And we'll talk about that in a second. So for acid-base neutralizations, though, the reaction, remember, the reaction is always going to be forced to completion, even if one of the acids is weak or the base is weak. And that's just because when you have a acid reacting with a base and neutralizing it, it's going to force the other one to give up force the acid to give up its protons. So this is a basic schematic of a titration over here. We have a burette, and this is the apparatus we put our titrant or the standard solution into. And we're going to use this standard solution inside that burette and add it to the analyte, a beaker or a flask actually, with our analyte. And the analyte is also known as the titrand with a D at the end. And the analyte we do not know the concentration of. So what we're going to do is we're going to slowly add our titrant or standard solution into the analyte until we have a color change. And that color change we often we find that color change using an indicator, and this is a substance that causes the solution to change color at certain pH values. So really there's different indicators with different ranges of color changes and when they do change colors and when they don't, but a common one used for acid-base neutralizations is phenolphthalein, and the reason that's used pretty frequently is that phenolphthalein is colorless when you have an acidic solution or neutral, but as soon as that solution becomes even slightly basic, it starts to become a reddish pink. It's like a magenta color actually. So the reason this pH range where it changes color is so useful is because if let's say you're titrating a weak acid with sodium hydroxide, a strong base, or strong acid even, when you're adding that when you're adding the strong base into the acid, it's going to continue to slowly neutralize it. And once it reaches that neutral, and once it becomes slightly basic, it changes color. And then at that point, we know it's going to be the end of the titration. So that's the equivalence point. It's a point in the titration where the acid has been completely neutralized, and that's by adding the sodium hydroxide in the example I just gave you. And there is a distinction, however, between the end point of titration and the equivalence point. So what the exact distinction is pretty subtle, but the end point is the point in titration where we have a color change occurring. So that color change occurring does not technically necessarily mean that is the point where it's equivalent, right? Because we can have other indicators as well. Usually with phenolphthalein, the whole point is that the endpoint is very, very close to the equivalence point. And because of that, we can determine the concentration. So once your endpoint is reached, that indicates that you've reached the equivalence point between the acid and the base. So the volume of the titrant you added can then be used to determine the concentration of analyte, right? If you have an acid and base, to completely neutralize it, it should require the same number of moles of acid and base, assuming they're both strong. So the last kind of topic that we're going to be touching on is with chapter 10. This has to do with energy changes and enthalpy of reactions. So chemical reactions, they involve breaking and formation of chemical bonds. So if you remember back early on in Gen Chem 1, we talked more about transitions of electrons in the Bohr model. So you know that when these electrons they're absorbed, they release energy, and when it takes energy to excite them. So similar to that, we have it with bonds. So when you're breaking a bond, you require energy input to break that bond, and to form a bond where it's going to release energy. So a chemical reaction, as you know, is a reaction that involves a change in chemical structure and change in chemical bonds. So for any chemical reaction, you have both breaking of bonds and you have forming of bonds. And each of those has different effects, right? You have absorbing energy or releasing energy. So the balance between breaking and forming bonds is what determines the overall energy changes that occur in the reaction. If you have a reaction that absorbs more energy than it releases, it becomes endothermic. If you have a reaction that releases more energy than it absorbs, it becomes exothermic. So heat is the transfer of energy between two bodies of different temperatures. So this involves system and surroundings, right? If you touch a really cold floor with your feet, you have a transfer of energy, and that's essentially an endothermic reaction in a way. A transfer of energy between the floor and your feet. So the floor could be considered your surroundings, and your feet can be considered the system. And the whole reason why your feet feel so cold on that cold floor is because you have heat going from your feet to the floor. It's being lost. Yeah. Okay. So enthalpy of reaction, this is going to be one of the main factors that really calculations are involved in this unit so far with energy changes. But under constant pressure conditions, the enthalpy of reaction, or delta H, is basically used to determine the heat exchange that occurs in the reaction per mole. So delta H is also the enthalpy change from the products minus the reactants, right? So that gives us an overall state function to work with. When we have, this is just the positive delta H versus negative delta H. This is essentially just a convention. It doesn't actually matter whether it's positive or negative, but it allows us to indicate whether a reaction is endo or exothermic, right? So if the enthalpy of your products is greater than the enthalpy of your reactants, that gives us an endothermic reaction, right? Looking at that first equation we have over here for delta H. And what that's saying is that the enthalpy, which is a thermodynamic function, and it has a proper definition, of which this is getting a little bit, more into thermodynamics, so I don't want to get too far into it. But you can treat it like energy for now. So if we have something higher energy, higher enthalpy in our products, and then in our reactants, then we're going to have an overall gain of energy, and that's going to become an endothermic reaction. Vice versa, if you have an exothermic reaction, is when the products have less enthalpy than the reactants. And that's why exothermic reactions, you have a lot of heat released, you have a lot of energy escaping. So thermochemical equations, this is basically just a normal chemical equation, except the difference is that you have a delta H value associated with it. So in this one, you have CH4 plus 2O2 gives CO2 plus 2H2O. And the delta H associated with this reaction is negative 890.4 kilojoules per mole. What this reaction is telling you is that for each mole of carbon dioxide formed in this, we're going to have negative 890.4 kilojoules of heat released. Remember, it's negative. What that means is that it's an exothermic reaction, meaning heat is being released. And then as well, for every 2 moles of H2O forming, we have negative 890.4 kilojoules released. So just remember your stoichiometry when you're dealing with these. Okay, we are ready for breakout rooms.
Okay, here we go. Moving to the first question. So balancing the following chemical equations. So we just have 3 of those, and let's go ahead and try balancing them. So let me see. Let me open up a whiteboard real quick. Okay, share my whiteboard. Okay, so I'll rewrite what the first part. So we had initially NH3, right, plus CuO yields Cu plus N2 plus H2O. Okay? And so let's go ahead and look to see what we have on both sides. All right. So it looks like if we're looking at, this is a copper, Cu. We have both, I'll pull out my pointer. A Cu on both sides, right? So there's one Cu here, another Cu over here. So it looks like we're good here. Let's look at oxygen, right? We have one oxygen here, we have one oxygen there. So far, so good. Let's take a look at nitrogens next. So we have a nitrogen here, then two nitrogens here. So looks like we're going to have to change a coefficient. And let's go ahead and add a 2 here so we can have two nitrogens on both sides. Okay. So has that changed anything else that we have here? Copper, pull out the pointer again. Copper remains the same. Oxygen is also the same. But it looks like it changed up a bit of our count here for hydrogen, right? 2 times 3 is 6. So we also need 6 hydrogens over here. Therefore, we're going to need 3 on this side. So we have 6 hydrogens total. Okay, so our hydrogens are balanced. But it looks like it's also going to affect our oxygen count over here. So now we have 3 oxygens. So to have 3 oxygens on the reaction side, right, we need to play around with this guy and give us 3 oxygens here. And now that we also had copper in our compound, that's going to change up our count. So now we have 3 coppers on the reactant side. Three coppers on the reactant side, and we're going to have 1 copper on the product side. So to balance that out, let's go ahead and put a 3 here. So now everything else should be good. So let's go ahead and double check. Just did. Let's look at nitrogen. We have 2 nitrogens on the reactant side, 2 nitrogens on products. We're good here. 6 hydrogens on the reactants, 6 on the products. Good here. 3 copper. We're good. 3 oxygen and 3 oxygen. So it looks like a perfectly balanced equation to me. All right. Did anyone have any problems with this one? No? Okay. So let me go ahead and clear the board and go back to opening that file. Well, I think it might be faster if I just share my screen instead of scrolling through all the slides. Okay. So the next one, right, we have KClO3 yields KCl and O2. All right, so I'm going to have you guys start off with this one. And tell me what you guys think we should do. Let me write it out. And O2. Okay. You guys can go activate your mics or go ahead and text in the chat. Balance the oxygens first. Okay, yeah, let's go ahead and do that. Okay, so it looks like we have 3 oxygens on this side, and we have 2 oxygens on the product side. So what's a common denominator? So I think someone said 6, right? So to get to 6, we're going to need 2 over here. And to get to 6, we're going to need 3 on this side. Oh, looks like it came out weird. 3 on that side. Okay, so we have 6 oxygens now on both sides. It's balanced. All right, yeah, exactly. So now that we have oxygens we're taken care of, we look at KCl's, I guess. They're already both here. So we have 2 Ks here, 2 Cls here, and 1 K, 1 Cl. And luckily for us, it's an easy fix. Just put 2 there. All right. That one's good. Let me go ahead and write the next one. All right. Next one starts off with a, oh my gosh, sulfur, right? Plus HNO3 yields, I'll write it down here, H2SO4 plus NO2 plus H2O. All right, so how do you guys want to start this one? Typically, I like to start it with, you don't want to look at the hydrogens or first if you don't need to. You want to typically start with like a larger atom. So I would start with sulfur. In this case, sulfur is just one on both sides, so pretty easy. And then next I would look at nitrogen next because it's the second heaviest. So again, that one's not bad either. There's one on both sides. So now I would start looking at oxygens next. This one is definitely pretty tricky. So let's go ahead and take a look, see, right? So we have 3 oxygens on the reactant side, and we have 4 here, 2 here, 1. So it looks like we have 4 plus 2 is 3. Okay. I think this one will be kind of tricky. So go ahead and just take a look at hydrogen instead, right? So that might be a little easier to just go to hydrogen. So we have only, let me put on the pointer. We only have 1 compound that contributes to hydrogen on the right side. Sorry, the reactant side. And then we have 2 compounds that contribute hydrogens on the other side. So taking a look at this one, I would probably want to put 4 right here for the time being. So we have 4 hydrogens on both sides. So how does that change things up, right? Well, that's going to make sure that our number of nitrogens is now different. So we now have 4 nitrogens on the reactant side, so therefore we need to have 4 nitrogens on the product side. Okay, and so let's see how that changes our number of oxygens. Now our nitrogens are balanced. So far, our hydrogens are still balanced. So we have 4 times 3, so we have 12 oxygens on the reactant side. See how many oxygens we have on the product side. We have 1, 2, 3, 4, 4 and plus 8, 12. 4 plus 8 is 12. And then we have 1 more, making it 13. A little tricky. Yeah. So what do you guys think that we could do? Did I put this one in correctly? Okay. So definitely our oxygen's a bit off. So I think it'd be easier if, let me go, we go ahead and try and convert this oxygen, into a positive number. An even number instead. So let's go ahead and try writing a 2 in here for now. Okay, so now that we have 1, 2, 3, 4, 5, 6, right? And get rid of this guy. Yeah, let's go ahead and move this one over here. I'm not sure how to delete it. Sorry. Hang on with me for a second here. Okay, so let's try that balancing again. All right, so now that we have a even number over here, let's see. We have even number of oxygens, so let's see our number of hydrogens this time. So 1, 2, 3, 4, 5, 6. So it looks like we have 6 hydrogens on this side. Let's try 6 over here. See how this one works. All right. So we have 6 hydrogens over here. So let's see how many oxygens that we have. So if we put that 6 there, then so we have 6 nitrogens right here. So we're going to need 6 nitrogens in the reactants product side. So let's see how many we have now. We have 4 oxygens on here. So our nitrogens are now balanced, so we're looking at oxygen instead. 4 oxygen here. We have 12 over here. So for 12, 16. 16 plus 2. Let me just double check my math is correct. 4, 12, and then 2. So yeah, this will be 16, and then plus 2. That's going to be 18 oxygens. All right. So our oxygens, go ahead, pull out that pointer. We're going to be balanced over here. We have 6 times 3, 18. And as I just showed you, we also have 18 oxygens on the product side as well. And our sulfur is balanced. We have 1 sulfur on both sides of the reaction. And checking again with our nitrogens, we have 6 nitrogens on the reactants, 6 nitrogens on the products. And double checking with our hydrogens, we have 6 hydrogens on the reactant side, and we have 1, 2, 3, 4, 5, 6 on the product side. So this one definitely was tricky. I made sure I chose specifically a harder one to try to do. But sometimes you'll have to try different methods to see what it takes to find out the perfect coefficients to balance everything. So did anyone have any questions over this one? All right, I'm gonna go ahead and clear the screen and go on to the next equation. All right, I'll share my screen real quick. All right, so you want to identify the types of reactions in each of the following equations. So I think it's probably just easier to just share my screen while walking you guys through this one. Just go ahead and pop open, just type out what you think the reaction is. So again, we have 5 types of reactions. We have combination reactions, also called synthesis reactions. We have decomposition reactions, the opposite of that. We have combustion reactions, single replacement, and then double replacement. So go ahead and type in the chat or just turn on your mics if you would like to. And tell me what you think the first one is, and then I'll just pop up to the tab to read your answers. What is the first one? Combustion? Yes, exactly. So an easy clue to figure out if it's a combustion equation, you want to look at one of your reactants. If you see oxygen, you're going to need oxygen for a combustion reaction. So this is already an indicator that this may be a combustion. Next, you want to look at your products, right? So you have your products are going to be water and carbon dioxide. So this further confirms the fact that this is indeed a combustion reaction. So awesome job. So this typically, whatever reacts, it's going to be comprised of carbon, hydrogen at the very least, and sometimes it has an oxygen within the molecule, but it's like a large molecule usually. Okay, let's move on to the next one. If anyone has any questions, feel free to text in the chat and I'll hop over. I hear the ding and take a look at it. Okay. What about the next one? Decomposition, exactly. So we have one molecule and it breaks apart into smaller molecules. So there's like two types right here. So split apart basically. All right. Moving on to the next one. Silver nitrate reacts with nickel and it forms nickel nitrate and silver. So which one is this? Single replacement, exactly. Excuse me. We have a single metal, nickel right here, right? It's swapping in with nitrate. So it's like trades partners. It kicks out the silver and it forms this new compound. So that's why it's considered single. It could also be a redox reaction. I think it would be. Yeah, so because initially the silver is giving its electrons to nickel, or to the nitrate. In this case, we're only thinking about the 5 reactions, like the 5 basic reactions. So just keeping it to the 5 basic reactions, you want to just consider it to be the same replacement. I think you might be right in the idea that this is also involves the transfer of some electrons, and it can also be considered as a redox. Okay, moving on to 4, if there's no any other questions. What type of reaction is number 4 out of the 5 that we mentioned? Okay, double replacement, exactly. So we have this initial compound, it's like calcium acetate, I believe. And so these anions swap places, so you see that. And then these cations swap places, anions also swap places. So why we look like that? It's going to be a double replacement. Exactly. What is the last type of reaction we need to know? Okay, so there's 5 main basic reactions, right? We have combination, also called synthesis. So you have like multiple reactants and they form a single product. It's called combination or synthesis reaction. We also have the opposite of that, which is decomposition reactions. We have one reactant breaks apart into multiple products. Then we have a combustion product, combustion equation, which is like the first one where we were doing. The combustion, you have a compound, and it reacts with oxygen and heat. The heat will typically not be in the equation. And it forms carbon dioxide and water. So those are indicators for combustion reaction. You have water and carbon dioxide as a product. And then next you have single replacement. wherein one ion replaces another. You have double replacement where two ionic compounds will basically swap their partners. So the cations both switch their partners with the two different other anions. Does that answer your question? So the one not mentioned here would probably be the synthesis one. Yeah, I did not include a synthesis one in here. Okay, and there's no other questions. So feel free, even if I move on, like go a little too fast, if you throw your question in there, then I'll still read it. We can go back a bit if we need it. All right, so let's take a look at this one. If we have 4.95 grams of ethylene, so it's important we write out that formula, C2H4, it's combusted, right, with 3.25 grams of oxygen. So what is the limiting reagent? And then how many grams of CO2 was formed? So what kind of equation do we have, or what kind of reaction? Can you guys tell me what kind of reaction we have? Exactly, combustion. The idea here is that, yeah, it reacts with oxygen, and they tell you, they're asking you how much CO2 is formed. Okay, so they gave us all the reactants and products we need. You know, since we know it's a combustion, we're going to have water. But they didn't give us any coefficients, so that's what we have to figure out. So let's go ahead and balance this equation. So how do you want to balance it? The one want to balance it, so I would typically, again, leave hydrogen and oxygen to the back end, and so start looking at the other atoms. So let's look at carbon first, so it's not hydrogen or oxygen. So we have 2 carbons on the reactant side, and we have 1 carbon on the product side. Therefore, we got to change that coefficient to 2 here. Right, so now we have 2 carbons on the left, 2 carbons on the right. Let's take a look next. Let's see what we've changed. So it looks like we've changed the oxygen a little bit. So let's go ahead and figure out what we're doing with the oxygen. So let's see. We have 2 oxygens on the right-hand side, and also have, looks like 1, 2, 3, 4. So we have 4 here. Oh, sorry, let me put on the pointer. 4 here. We have 1 here. Looks like we have an odd number, right? That's not going to jive really well if we have an even number right here. So let's go ahead and try to convert this oxygen to be like this molecule to have an even number of oxygens. So let's go ahead and throw a 2 in here. Okay. So if we have a 2 in there, see how that changes up our oxygen count. Oops, sorry. Oxygen count here. So we have 2 oxygens here. We have 1, 2, 3, 4. So we have 6 oxygens total. Go ahead and give us a 6 right here. I mean a 3 here, so give us a 6 total on the reactant side. But as you noticed, I put a 2. I'm going to pull out the pointer again. Put a 2 over here. So that means it's going to affect our hydrogen count. So we have 1, 2, 3, 4. We have 4 hydrogens right here. And turns out we also have 4 over here. So it looks like things are balanced. We're good to go. So let's go ahead and do the rest of the problem. So we're asked what is our limiting reactant. Let's go. I'm going to go ahead and write out how many grams we have. We have 4.95 grams of, I think it's called ethylene, and then we have 3.25 grams of oxygen. So the way I like to figure out the limiting reactant I'm going to go ahead and choose one of the reactants. Let's go ahead and just convert. Let's convert both of these guys to moles. That makes it easier. We have 4.95 grams of C2H4. 1 mole. So what's the molar mass here for C2H4? So I typically round when I'm doing mass. It shouldn't make a significant difference typically. So carbon I consider to be 12, and hydrogen I consider just to be 1. So 2 carbons, that's 24, plus 4 is going to be 28. See what we get there, and then if someone can put that in their calculator. 5 grams of oxygen, 1 mole, and that's 16 grams. Thank you. Thank you, Melanie. 767 mole of C2H4. And then let's go ahead and convert this guy, if anyone can write that out. See, I almost made a mistake here. Notice that this is O2, so that means there's 2 oxygens, right? So we can't have 16. Just gonna throw that over there. You need to have 32. All right, make sure that you have to keep in mind whether or not an atom is diatomic. So your diatomic ions, or sorry, diatomic atom, like hydrogen, oxygen, chlorine, fluorine, iodine, and bromine. So the weight is going to be doubled if you're dealing with a diatomic. So can someone tell me what this number is? Awesome. Thank you, Lauren. 0.1016 moles oxygen. Okay, so at this point, I like to do a ratio. So let's take a look at our ratio up here. So we have basically 1, right? A 1:3 ratio. So that means, go ahead and choose. Oh, so that means basically we triple the amount of oxygen for however many moles of C2H4 that we have. Basically, if we triple the number of C2H4, that's how much oxygen we need in order to react this fully, right? So we need basically 3 times 0.1767 moles of oxygen. We have that? We have that amount? Okay, all right, thank you, Lauren. Yeah, I was going to need 0.5301 moles oxygen. Yeah, so definitely we don't have enough. So we're going to go ahead and say that, hey, if we don't have enough, that's going to be our limiting. So this means this is our limiting reactant. I'm going to call it LR. All right, so that's the first part of the problem. So the second part was asking us how many grams of, this is how many grams, let me double check. How many grams of CO2 are formed? So what can we do from here? Let's go ahead and convert, right, our moles of oxygen, our limiting reactant, into grams of CO2. So how can we convert it to grams of CO2? If we're in moles of oxygen, what can we use? Yes, exactly, the mole to mole ratio. So luckily for us, we balanced the equation earlier, and this is one we're going to be using our mole to mole ratio. Basically, looking at oxygen compared to CO2, it's a 2 ratio, 3 to 2. That's going to be important. All right, so our moles of oxygen have to be at the bottom, so they cancel out, right? We have 3 moles of oxygen, 2 moles of CO2. All right, so now we're in terms of moles. Our units are going to be moles of CO2. So to get to grams, like you guys probably guessed, you're going to need mole and gram. So you're going to use the molar mass of CO2. Just from doing it for so long, I memorized it. It's 44 grams. It should be 44 grams. Yes, okay, I just did it in my head again. All right, yeah, it's basically 32 plus 12, 44, and 1 mole. But again, you probably guys don't have it memorized, so go ahead and add that up if you need to on the day of the exam. Okay, and so everything else should cancel. Let me go ahead and change different color. Bang, bam, bam, bam. So I should be left with grams of CO2. Can someone tell me what that is? Multiply everything on the top, divide by everything on the bottom. .98 grams of CO2 was produced. Thank you, Melanie. All right, awesome. Did anyone have any questions or get lost along the way that I was going through? I know I went through that relatively quickly. Okay, so if there's no questions, I can go ahead and move on to the next question. All right, I'll go ahead and clear the board. And I'll share my screen with y'all. Yeah. The next one. All right, so let's take a look at this one. So we have 85.4 grams of chlorine. Right? Chlorine should be Cl2. Remember, chlorine is one of your diatomics. Remember that. That's why they told us the molar mass is going to be 7.91 grams per mole. And they're using that reaction. So P4 plus 6Cl2 yields 4PCl3. Right? And they're telling us in a lab setting, right, they produce 104 grams of that product. And they're asking us what is the percent yield. So I'm going to go ahead and go back to the whiteboard. So how do you guys want to approach this? Let me go ahead and write. You guys can tell me what your initial approaches are going to be. I'll just write out what we have. Balance. Okay, that's good. So far, actually, they gave us a balanced equation. I'll go ahead and write that out. So it's P4 plus 6Cl2 yields 4PCl3. So I would definitely agree with you if I was unbalanced already, but so far it's already balanced. They gave us that. So what should we do from there? Convert the Cl moles. All right, I like that. Okay, so we have 70.91, right? To convert to moles, you want to use the molar mass. So 1 mole of Cl2. Okay. So what do you want to do next? So it looks like we have our units in moles, but what are we actually trying to do? What are we trying to get at the end? Good. So the next step we want to do is use the mole to mole ratio. Figure out how much moles of the P3 we want to next, right? So looking at the mole to mole ratio, let me pull out my pointer. We have 6 moles of Cl2 for every 4 moles of, I forget what this compound, let's call it the product. So let's go ahead and write that out. So we have 6 moles of Cl2 for every 4 moles of the product, Cl3. So should we stop there or should we keep going? What are the moles to grams? All right. Multiplied by the molar mass of PCl3? Yes, exactly. So let's go ahead, figure out the molar mass. 1 second. 1 mole. PCl3. I think they gave it earlier. Right, it's 137.3. Let's go ahead and write that out. You guys need to look it up. 137.3 grams is PCl3. So can anyone tell me what that is? Multiplying everything on the top. $248.034 grams of PCl3. Okay. Anyone else also get that answer? Okay, so what should we do from here? Where should we go from here? Percent yield is equal to actual over theoretical. So wait, so let me double check calculations real quick. Okay, yeah, it should be 110. That's what I was double checking the key. No worries. Sometimes it just happens sometimes. Don't worry about it. Go ahead, cross this one out for a second. Okay. Equals 110. I forget what the remaining digits were. I'll double check. 100.10.2. 0.2 grams of PCl3. All right, and so like you said earlier, percent yield is actual over theoretical, right? So our actual is 104. We're going to put over theoretical 110.2, and then just times 100. And so what does that give you guys? %. Awesome. Thank you, Miriam. Okay, did anyone have any problems with this one? So the main idea, again, they give you the amount of reactant, and you want to go ahead and balance the equation if it's not balanced yet, and then convert that reactant all the way to your product, and that's going to be your theoretical amount, and go ahead and place that in your denominator, and whatever your actual will always be given. You place that over your theoretical, and then times 100, you'll get your percent yield. There's some other ways they could do a percent yield problem. They could potentially tell you the percent yield and might ask you how to figure out the actual. So just kind of working backwards. I think that would be like the hardest they would come up with a percent yield question. All right, go ahead and clear the board now. No one has any other questions, and we can move on. Oh, okay, here we go. Oh. Believe we were on question 5. All right. Okay. This one probably be easier just to talk through it. Don't need to write anything. So it wants us to identify how many ions each of the compounds dissociate into, and then how many of these guys are, or which ones are non-electrolytes and which one are electrolytes. Let's go through the first one, right? If NaCl, how many ions would that dissociate into? Yeah, exactly. It should just be 2. You have Na plus, Cl minus. So you'll just have to kind of practice to see what kind of ions that are most easily identified. How about the next one? How many ions does it break apart into? Okay, looks like I heard some responses. Not exactly. It's going to be a non-electrolyte. I believe this is, exactly what molecule this is. But typically, if you see a molecule like CHO, it's going to be it's not going to be ionic, it's going to be a covalent compound, and it will not dissociate into ions. We don't see any metals in here, so that's another indicator that it's not an ionic compound. Okay, let's go ahead and move on to the next one. Send any questions as needed. I can double back whenever. Okay, what about K3PO4? How many ions does that break apart into? Okay, looks like I'm hearing responses. Let me see what you all said. Exactly, so we're going to have 4 ions. So the potassium is going to break it up into 3 potassiums, and then we have 1 phosphate group. So it's going to be 4 ions. Okay, what about the next one? This one's a little tricky. I'll give you that as a hint. Exactly, so it's going to be actually going to be 2 ions. So you might think it's 3 because there's 2 hydrogens and 1 sulfate group. However, it's going to be 2 because if you guys remember from the lecture portion of the review session, we said that sulfuric acid, this is H2SO4, is a strong acid, only on the first protonation. So once you break apart into H plus and HSO4 minus, those 2 guys, the HSO4 minus will not want to break apart again into SO4 minus and H plus. So it only wants to dissociate 1 time. It breaks apart into those 2, and that's typically it. That's why it's 2. Yeah, exactly. There's only going to be 1 hydrogen and then 1 HSO4 minus. Okay. Moving on, what's the next one? How many ions does it break apart into? Three? Yes, exactly, three. You're going to have it's barium hydroxide. Barium has a 2+ charge, and hydroxide has a 1- charge. So it's going to have 3 ions total. It breaks apart into 3. It's one of your strong bases that you need to help summarize. I believe there's about 8 strong bases and then 7 strong acids. Okay, what about the last one? None. Exactly. It's going to be a non-electrolyte. Again, being able to identify whether something is an ionic compound or a covalent, how to differentiate whether it's going to be an electrolyte or not. So CO2 is going to be a covalent compound, does not break apart into ions, so it's going to be a non-electrolyte. So other ways to identify if it's an electrolyte, again, ionic compound, whether or not it's a strong acid or a strong base. So identifying, memorizing the 15 strong acids and bases, 7 strong acids, 8 strong bases, and then identifying if something has a metal that makes it an ionic compound. What about HF? Would it dissociate? So HF, yeah, exactly, it's a weak acid. So it would dissociate, but it would not dissociate into 2 ions specifically. So not all of them will dissociate into 2. So an idea is like the average dissociation could be fluctuate between 1 and 2. So it might be like 1.5 ions average in there. So typically, we want to, when we're thinking of strong electrolytes, we want things that dissociate completely. And those are always going to be strong acids, strong bases, and ionic compounds. No problem. Okay, moving on to 6. So let's write out a reaction, right, for HClO3 and NH3. And then identify which is the acid and what are the products that they create. And identify if any of the reactants are strong acids and bases. So I'm going to go ahead and write it out for y'all. Or I'll help set it up. Okay, so we have HClO3 plus NH3. What should it yield? What are the products? H2O is one of them. Not necessarily in this case. So H4 and ClO3. Yeah, that's correct. Don't forget the charges, NH4 plus and ClO3 minus. Okay, so the idea, Melanie, behind the water. So typically whenever you're doing like an acid-base reaction, so you want to have some kind of compound. Yeah, this is what I'm getting to. So this is the general formula. So when you have an acid and base, typically your base needs to have a hydroxide group right here. And your acid is always going to have a group. So when you're reacting them, you're going to basically swap partners. It's going to be like a, what is that called? Double displacement. So you have an HB, or sorry, an AB. I guess it makes sense more as a BA plus H2O. Or HOH, if that makes more sense. So the H combines with the OH, that basically is H2O. And this is your salt. So this is what would happen if you have a base that looks like this. Yeah, so since ammonia doesn't have a hydroxide group, it will not form water. No problem. So going back to this one, is everything balanced? Yeah, so everything should be balanced. It's all good. Let me see what we were doing. Right. So identify what is the acid and base. I think like you guys already pointed out that NH3 is already a base, right? Base. And so that just leaves this guy as the acid. Awesome. Any other questions over acids and bases? Okay, I'm going to go ahead and move on, all right? Okay, go ahead and move on to the next question. Go ahead and share my screen, right? All right, so the next one, they want us to write out the complete ionic and net ionic form for these reactions. Excuse me, let me get another piece of paper. That's not going. Okay, this one's good. Okay, let me just write it out real quick so I can transfer it to the whiteboard. You guys can try writing it out on your own and on like scratch paper or something, and then let me know what you guys got in a bit once I worked through it. Okay, so between iron 2 sulfate and between chromium 3 sulfate, so should be in reaction arrow. All right, go ahead and share my board. Go ahead and write it out. So we have magnesium nitrate. So that's aqueous. plus sodium carbonate. It's also aqueous. Yields, I'm going to write it down here. Magnesium carbonate, solid, and sodium nitrate, which is aqueous. So is this equation balanced? Exactly, no, it is not balanced. So go ahead and balance it. What can we do? Let's see here. Looks like our sodium count is off, right? We have two sodiums on the left, one sodium on the right. So let's go ahead and double that sodium concentration. So it looks like that solves, yeah, looks like we're balanced now. Good. So let's go ahead and this guy up into the ion forms so we can get our complete ionic equation. So magnesium breaks apart, right? As you can see, if you guys remember from the periodic table, it has a +2 charge. Plus our nitrate. Since we have two of them, we should write up 2 NO3 minus. Plus our sodium, we have 2 of those. Plus we have CO3. So that's going to be 2 minus. So again, that's one of those polyatomics you need to memorize. So that produces what? CO3. Solid. And go ahead to Na2 plus aqueous, right? So anything that has an aqueous sign, state sign, I'm going to break it into ions. I didn't break apart magnesium carbonate because it is a solid, right? It does not break apart into solution. If it's already in solution, it didn't break apart, then it's not going to break apart. Anyone have any questions over this complete ionic equation that we wrote? Okay. Cool. So let's go ahead and figure out what are spectator ions to make a net ionic equation. What are our spectator ions? So let's take a look on both sides, right? Looks like we have sodium on both sides, and they're both aqueous. Right, yeah, it would be nitrate and sodium. So crossing those guys out as our spectator, what's left behind is going to be our net equation. So this, and okay, did anyone have any trouble with this one? I'm going to go ahead and do the other one for y'all. Should last 10. So I'm trying to cover as much ground as we. Of course, no problem, Hussam. Good luck with the exam. So for the next one, we have, let's write it out. Chromium. Oh, Mr. Nem. Let's get our head right. Chromium 3 nitrate. Reacts with iron. 2 sulfate, yielding chromium three sulfate and iron. Sorry, it should be parentheses here. 2 nitrate. So that was our question stem. Let's go ahead and convert that into a chemical equation. Right? So what should that be? So we know chromium has a +3 charge, right? It's a transition metal, so they've given us a charge of 3. How many nitrates do we need to balance that? So we're going to need 3. So these were aqueous plus, what about iron sulfate? Iron is a +2 charge. How many sulfates do we need? 1. Exactly. This guy's going to be aqueous again as well. Yields. What about next one? Chromium 3 sulfate. This is chapter 9. I forget which chapter. I know you guys talk about ionic and net ionic. I believe it's chapter 9. I know it'll be on the exam, the next exam. Sure. Being able to identify a net ionic equation. So you have chromium, right? 3 plus. But then sulfate, if you guys remember, is 2 minus. So how should we approach that? Exactly. It would basically change, swap the subscripts or something. So 3, 2, and then 3. And again, these guys are both aqueous. And what about iron 2 nitrate? So we said earlier, nitrate has a -1 charge, so we're going to need 2 of those. This is aqueous. That's a doozy. So let's go ahead and break this guy down into the complete ionic form. Cr 3 plus, right? Q plus, looks like we're going to be 3 minus AQ plus Fe2 plus AQ plus SO4 2 minus AQ yields before we continue, is this balanced? Is the equation balanced? Familiar? We'll jump the gun there. Nope, exactly. So let's go ahead and see how we balance it. It looks like we have 1 SO4 on the left side and then 3 SO4s on the right side. So we should put a 3 right here. Right, so now it's balanced for SO4s, but we've also changed the number of irons on both sides. So make sure we put a 3 on this side. Alright, so our irons are balanced, but now that's affecting our nitrate number. So we have 3 here, 3 times 2 should be a 2 over there, we should have 6 nitrates. So that means we need to put a 2 here to get 6 nitrates on the reactant side. And now the chromiums are balanced. So these guys are now balanced. So go ahead and rewrite the coefficients. There's a 2 here, be a 6 right here. Should be a 3 here, and then a 3 here. Okay. So go ahead and write the rest of it. Do CR 3 plus AQ plus 3O4 2 minus AQ plus 3Fe2 plus AQ, and then plus 6NO3 minus AQ. All right, so that's going to be our complete net ionic. It's kind of a handful for sure. All right. So what will our net ionic? We have our complete ionic. What will be our net? Yeah, exactly, Miriam. There is no net ionic. Everything appears on the reactant as well on the product side, so everything will cancel out. We do not have a reaction going on here. These are all spectator ions. Okay, awesome. Any questions over this one? All right, I'm going to wipe the board. Oh, so none of them appeals, and none of them would be spectator ions. Let me go right. Did you mean this example specifically? The example we just did? Because the ones that we just did in a similar example. Okay. Well, in the example we just did, since all of them, let me go back to the equation. All of them are aqueous. They all break apart into ions, and so there should be no reaction because they're all spectator ions. If you do have the other example, you could send it to me, and I could take a look at it and see what your PLTL leader did. Okay, here I'll send my email real quick. Yeah, feel free to send it to that email, and I can take a look at it. All right, so moving on to number 8. We do have about, okay, so looks like there's only 14 questions total. So let's see if we can make it through all of them. Shouldn't be too bad. So let me write out this one. So looking at number 8, they want us to balance the equations and then see which ones are oxidized, reduced, and what the reducing agent and oxidizing agent are. All right, so let's go ahead and open up that whiteboard. Okay, so I'll write out the first one. Okay. Is this reaction balanced? We gotta balance it, right? So how do you want to balance it? So initially I would want to look at the iron, but it looks like the oxygens are doing that weird thing where one side is even, one side is odd. So we have to try to convert them. Okay, yeah, cool. Looks like that would probably be the answer. So I want to put like a 3 here and a 2 here. So we have the same number of oxygens on both sides. And now we just need to balance the iron, and it should be easy because we have one iron compound over here. So we put a 4. Okay, so taking a look at the oxidation numbers. Let's assign oxidation numbers for each of these molecules. So what's the oxidation number for iron right here? 0? Okay, awesome. Exactly. What about for oxygen? Also 0? Okay. Cool. How about iron in this compound? What about oxygen in this compound? Yeah, so oxygen's going to be 2 minus, and then iron is going to be 3 plus. So if you multiply by the subscripts, you're going to have a 6 plus total, and then a 6 minus total. That's why the overall charge is even. The 6 will balance out with the 6. But if we're looking at individual singular atoms, so we'll have each singular iron is going to have a plus 3. Each singular oxygen is going to have a minus 2. All right, so tell me, which one is reduced and which one is oxidized? Exactly. So iron here is oxidized because it went from a, they pull out my pointer, from a 0 charge to a plus 3 charge. So it became more positive. That means it had to lose electrons to. Versus oxygen over here was a 0 and it became negative. So it's going to have to gain electrons to do that. So that's reduction. We know what's oxidized, we know what's reduced. So what is the oxidizing agent? What is the reducing agent? Yes, exactly. So iron is the reducing agent. It causes the oxygen to be reduced. So it gave its electrons to oxygen. That's why it gained a negative charge. Versus oxygen is the oxidizing agent because it took the electrons and it caused iron to be oxidized. So that's the idea. So once you figure out which is oxidized is reduced, an easy way to go about it is like, oh, whatever is oxidized is the reducing agent. Whatever is reduced is an oxidizing agent. So that's the idea. Do you guys have any questions on this one? Okay. Nope. All right. I'm going to clear the board. I'm going to write out the next one. Let me do the next one real quick. So we have P4 plus O2, and that one yields P4O10. So let's go ahead and balance it. How should we balance it? Looks like our phosphoruses are balanced. Yes, definitely. Just a 5 right. All right, so let's go ahead and assign oxidation states yet again. What do we got for P4? Excellent, thank you, Suhas. Be 0. And likewise, this boy will also be 0, right? So what about for, go ahead and say oxygen. What is oxygen, oxidation state? 2 minus, right? So having 10 of those, you're going to have a 20 minus, right? So should also have 20 plus, exactly. So that should leave us with a 5 plus right here for each individual. So this is total. This is individual. Okay. How do you know when the exception for oxygen is present? It's not always 2 minus. Right, so it's not always. There's here. I'll pull up the exam. Oh wait, it might cancel it. Okay, but I'll show you in a. If you go back, you'll get a copy of the rules. There's a chart in your textbook as well. It tells you basically the order of what you want to prioritize. So fluorine is at the top. Fluorine always gets a -1 charge. Next are group A and group 2 metals. So they'll always have a +1 and a +2 charge, I believe. And it's hydrogen, so +1. And then it's oxygen, which is -2. So say you're combining a group 1 metal with 2 oxygens, right? Like, so you have KO2. Or actually, I'll give you one better. You have a group 2 metal and you have an oxygen. So think about barium oxide, BaO. So BaO, barium is in the second, has a +2 charge. Oh, wait, that one doesn't work. I'm sorry. You think you got it? Okay. No problem. But basically, if you have something that's higher in that priority, it's the charge first. Yeah, so good one. KO2. Wait, no one has a +1. Or H2O2 is a good example. So hydrogen is above oxygen in that priority group. So hydrogen's +1 charge is going to take effect. So having 2 of those means that it contributes 2 positive charges. So then oxygen needs to balance it by contributing 2 negative charges. And so there's 2 oxygens. Each of them has to contribute 1 negative charge. So in that case, oxygen is a -1 charge. So there's a few instances, not that many, but you need to know the exceptions and how they arise. Okay, awesome. So going back to this one, go ahead and answer it. So we know phosphorus went from 0 to +5, so that means this guy is lost electrons. Activity series. Yeah, the rules are something you'll have to memorize. I don't think you'll be given the rules on oxidation number assignment. Okay, so this one has to be oxidized. So that means this one is going to be reduced. It's easy. It's always easy once you figure out which one it is, and the other is just the opposite. So that means phosphorus is also oxidized, and phosphorus is also the reducing agent, and oxygen is also the oxidizing agent. So very similar to the previous problem. Okay, so we do have a little less than 30 minutes left. If it's all right with you guys, I'll just try to do a problem from every question so that we get through all the content. You guys get to see a chance to see all the problems. Okay, all right, exactly. This is what I was talking about earlier. So it's going to be table 9.5 in your book, chapter 9. Go a little faster here. Okay, so let's look at this problem. So we have equation Fe plus O2 get Fe2O3. And how many liters of water are required for the reaction to go to completion if 5 gram solubility of oxygen in water is, okay, we have 5 grams of iron. We need, assuming the action goes to completion, how many grams of product are formed? Okay, so it looks like we have excess oxygen. This one's a little tricky, but it's not too bad. It's not undoable. 5 times 10 to the negative 4 molarity. Grams of product, so grams B2 over 3. Remember to use balance equation. Alright, so I'll write down everything from the problem. So we have Fe, right, reacts with O2. So that yields Fe2O3. So let's go ahead and balance it. So it should be a 3 here, 2 here, and a 4. It's very similar to the other one we did. It's the exact same. And so now we know that we're given 5 grams of iron. 5 grams of iron. And we're looking about how many grams of product? 3. That's what we're looking for. And we know the solubility of water, I mean, oxygen in water, right? (2.5 times 10 to the negative 4 molarity). So that means the more water we have, the more oxygen will enter the water, and it'll react with the iron that's dissolved in there. So let's see how much oxygen we need. That's the idea. So one of the questions it's asking is, how many liters of water we need? That's the first initial question. Okay, so go ahead. I'll help walk you guys through this one. So let's figure out how many moles of water we need. Sorry, liters. So we have 5 grams, right, of iron. When let's convert it to moles. What's the molar mass of iron? Anyone remembers? (55). All right, I'll say 55.8 grams, right? So that's our moles of iron. So we also have 4 moles. So let's use our molar ratio. We have. So we have 4 moles of Fe, iron. We're going to have 3 moles oxygen. Can someone go ahead and compute that for me? How many moles of oxygen do we need? To react with the 5 grams of iron? All right, 0.0672. 2 moles of oxygen. Thank you, guys. All right, so guys, remember the formula for molarity is going to be moles 4 liters. Exactly, thank you. And what we don't know is how many liters we need. So we do know that we need 0.0672 moles. To get this solubility, we have to figure out what our moles, our liters is. So can anyone tell me what that is? I'll throw that in your calculator. Yeah, okay. 268.8 liters of water. That was a tricky one, but the idea behind how you want to do it. So you want to convert into, give you the solubility of water, oxygen and water. So you know that's going to be important. Right? You're going to need to do something with oxygen. And so the idea behind that was that you want to get the grams of the iron, you want to convert it to moles of your oxygen. And then convert that, set that equal to your molarity, and then figure out your liters of water. So next, asking us for grams of iron, of the product of iron oxide. So we have 5 grams, right, of iron, 1 mole of iron, and then 55.85 grams of iron. So what should we do next? We want to go ahead and do our molar ratios, right? Exactly. We'll have a 4 ratio and a 2 ratio here. And then we're going to have 4 moles Fe. And we're not quite done there. We have to do molar mass next. It looks like we have 1 mole here. And then we're going to do, let me just check what the molar mass is. So I'm going to say it's 160. Round it a little bit. 160 grams. Or what, you guys throw that calculator again for me? Yeah, so that's the general setup. Thank you, Melanie. So finding your product. So you want to just make sure you convert from your grams to your moles using molar mass, and then you can use molar ratio. Use your molar ratio to convert into your product to a different compound, and then use a molar mass to convert that into grams. Any questions here? Okay, go ahead and wipe the board. Okay, so for the following reactions, say if the reaction occurs, and if the reaction does occur, then write out both reactions. Yeah, okay, it looks like we're not be able to get through, might not be able to get through all of them. So let's do like 2 of these. All right, let's do the top 2. You have chromium, then 2 plus, right? That yield, then H2 plus Au3 plus. That yields what? The full redox reaction. Okay, so let's go ahead and do that on the whiteboard. Again, we have chromium plus zinc 2 plus yields. All right, so this one we're going to need to take a look at our activity series. Right? Let me go ahead. You guys should pull 1, 2. You can just find activity series on Google. Okay, so looking at the activity series on Google, the chromium is below zinc on the activity series. So zinc is more likely to lose electrons than chromium would be. So if zinc is more likely to lose electrons than chromium, will this reaction occur? Will it occur here? Should be no. No reaction. Right, so zinc's already lost electrons. It's not going to want to lose further electrons. So no reaction will occur. Awesome. So let's move on to the next. We have H. What was the other one? So zinc has to be higher than chromium. So in this case, if you look at the activity series, zinc is higher than chromium already. But it's already lost electrons. It's not going to lose any more electrons, is the idea. So you can be higher, but there can still be no reaction because electrons are already lost. So if zinc didn't have a +2 charge, zinc was zero, no, neutral, and chromium had a +2 charge, then the reaction would occur because zinc would transfer its electrons to chromium. So higher on the series means higher chance of losing electrons. Yes. That's the idea behind the activity series. It's more likely that you'll be oxidized. You should lose your electrons. But you only want to lose them if you have them to lose, right? So zinc already lost some. It doesn't want to lose any more. Good. Okay, let me double check to see what the other one was. Okay, it was H2. U3 plus. So will a reaction occur here? Let's take a look at our activity series again. So will a reaction occur? Yeah, exactly. So a reaction will occur. So hydrogen is higher in the activity series than gold is. So, and hydrogen has electrons to lose, and therefore it's gonna be a redox reaction that occurs. So let's go ahead and write out two half reactions, right? We have H2 yields 2H plus, oh my gosh, plus 2 electrons. And what's the other half reaction? AU3 plus. So it's got to gain 3 electrons, right? In order to make AU solid, AU neutral. But as you see, there's a different amount of electrons on either side. So this side has +2 electrons, this side has +3 electrons. So what can we do to balance it? We need to have equal numbers of electrons on both sides of the half reaction. Times 3 and times 2, exactly. go ahead and write that in. So we're going to multiply the top one by 3. So we'll have 3 here. Let's write that number out. Put 33 here, this number out. We have, sorry, it should be 6 times 36. And then at the bottom, we'll multiply by 2. Multiply by 2, you get 6. Multiply by 2, you get 2 there. So now our electrons will be balanced out. Let's go ahead and write it all out. So these guys should become 3H2 plus 2AU plus yields 6H plus and 2AU. And this would be our fully balanced redox reaction. Any questions on this one? This one can be kind of tricky. Understand redox reactions can be tricky. This one makes you have to use your activity series, determine whether or not a reaction occurs, and if it does occur, then you need to separate them into the 2 half reactions to see what one reaction is doing, breaks apart into, and what the other reaction is trying to do as well. And then you have to make sure that they balance, because they need to have the transfer of electrons needs to be the same. If one reactant is losing some number of electrons, then the other has to gain the exact same amount. That's why it was important that we had 6 on both sides. Okay, if there's no other questions, I think we can do one more if everyone's still willing. Go ahead and share my screen real quick. How many milliliters? What's the same? Let's do. Okay, number 12 is a conceptual one. So let's go through this one really quick. The purpose of adding an indicator at the start of your titration. What could happen if you didn't add an indicator? So the idea behind, okay, look, someone said response. Exactly, yeah. So the purpose of adding an indicator is that you will know whenever you reach your equivalence point or your point. If you didn't add an indicator in there, you would not know. There would be no color change, and you could go past the equivalence point and you wouldn't know. It would all remain the same color. Except, can't tell when the reaction is. Okay. Let me do this number 13, guys, real quick. There's one last one before we go. We had 0.2 molarity solution of NaOH from a starting solution of 20 milliliters of NaOH. Will be the total okay. So they're telling us that we have 20 milliliters of a 5 molarity NaOH concentration, and we're looking to make a 0.20 molarity solution of NaOH. And how do we do that? So what kind of problem is this? Is a better way to start it. So you have, yeah, exactly. It's a dilution problem. So you're going to use the M1v1, M2v2 problem equation. into V2. So M1. So let's go ahead and convert this guy into. Actually, you don't need to. As long as your volumes remain the same, then you don't need to change it. So we have 5 molarity here. You put 20 milliliters here, right? So equals 0.2 molarity. And then whatever your volume is in your second solution. So that's how you set it up, and it's all for X, and that would give you your total final volume in terms of milliliters, of course. If they're asking for liters, just go ahead and convert that. So I don't need anyone to call in your calculator as long as you understand the concept. That's good. Does anyone have any problems with this one? That's good? Okay. Awesome. Go ahead and clear it. Let me think of another one. The other ones. Looks like it's 10 o'clock. I'm gonna go ahead and I believe you guys will all get an email with the PowerPoint and the questions in them. So I did leave my email in the group chat. If you guys have any problems with going through the PowerPoint and looking on the questions, I think we only didn't do like 3, which was like number 11, actually we only didn't do 2, number 11 and number 14. They're kind of long. 14 is a longer one, but definitely shoot me an email if you guys are having trouble with either of them. But with that being said, I want to thank everyone for sticking around the whole time. And 2.5 hours is kind of long. But I wish you guys all good luck on your exam on Saturday. All right. Thank you guys for attending. Yeah. Everyone have a good night.